Okay, all right, let's start. So what we're going to do is a couple of problems related to BGT circuits. All right, so let's continue with the example that we did in the last lecture. We took it as 5 volts. We put an RB here. RB here, we set 430K. And let's take RC equal to, let's increase the value a little bit, 2K. Let's add a load resistance, RL equal to 2K. Let's call this V0. Let's add an input, Vs here. So that's our circuit with some sinusoidal voltage also applied, or a signal voltage also applied. And let's give the transistor characteristics as beta as 100, early voltage as 100 volt. Let's put Vt thermal voltage as 26 millivolt, and that's it for the moment. Let's call this Cc here. Let's call this Cb here, and let us assume that the frequency here f is such that Cb and Cc can be considered as shorts, right? So this is the circuit that we have. What we would like is to obtain several things, starting with we would like to obtain V0 by Vs. That's the starting thing that we would like to find out. What is V0 by Vs for a circuit like this? Alright, so remember the way we do it is the circuit has DC plus a DC voltage is applied here. DC is like 5 volts and all that, and it has a sinusoidal voltage. So the output, we will calculate output. So we do DC analysis to figure out, to give us IC, DC current, base current, and all that, DC voltage here, all these things here that you know, DC quantities. And the sinusoidal we obtain using we have sinusoidal quantities like V0 and maybe other things. V0, sinusoidal IC, sinusoidal IB, all these things that are there, we obtain through small signal analysis. Okay, small signal analysis. So we break the analysis into two parts: DC, to obtain the DC currents, voltages, and all that, and then a incremental circuit analysis. This is nothing but small signal analysis is also incremental. So this is an extra voltage that we've added and we want to find out. This is also called incremental circuit analysis, right? It's a small signal analysis is a kind of incremental circuit analysis. So we'd like to do this to figure out V0 by Vs first. Now note that V0, both V0 and Vs are small signal quantities, sinusoidal quantity, SS, small signal. So in the last lecture, we had already done DC analysis. DC analysis was already done. And if you recall, it gave us IB equal to 10 microamperes. It gave us IC equal to 1 milliampere. And in this case, it will give us VCE equal to 1 milliamperes into 2, so 2 volts, so it will give us 3 volt. So we have all these, we had done this in the last lecture. All these things are known. So in today's problem first, what you do is you do the small signal analysis. Alright? You have to do the small signal analysis, and please do it on a separate sheet and submit also. A sheet which you would, I would want you to write your name, roll numbers, and submit also. Remember, all analysis is done by substituting the small signal analysis, or incremental circuit analysis will be done by substituting incremental circuit model for all the elements, right? So remember that the DC voltages will become shorts, transistor will be replaced by small signal model, capacitors we are saying is short at that frequency. Okay, so the first step is what? First step, what do we have to do? Obtain the small signal equivalent circuit, right? Obtain small signal equivalent circuit. Small signal equivalent circuit. That's the first step. How do we obtain the small signal equivalent circuit? What are the steps that we do? First step, independent sources are ground, right? So we remove this, we put it to ground. VCC is no longer there. Independent sources are ground, correct? Okay, then? So then we said frequency is such that the capacitors can be considered as short, right? So we short this. Vs, we short it. We short this and we short this. we short it, right? RL. Fine, that step is done. Next step is if you want at this stage, what you can do is you can simplify it, right? Simplify it. So obtain equivalent circuit. First step, independent voltage source becomes ground. Capacitors are shorted. If you want, simplify the circuit at this stage, because once you short and all that, simplify. So the simplification that we do is we remove, for example, here, we could just put RB here. Why put it there? Makes it easier. RB here, and all this we remove, and we can put here. We could see that it is RC parallel RL. Okay. The next thing is we substitute SS model of transistor, SS model of BJT. So we take our BJT out, we take it out, but we keep in mind that this is the base, this is the collector, and then there was emitter here, and emitter was ground. So we take the transistor out and we put the model. So model was R pi here, and GMV pi, and there was here R0, right? We have R0 here also. Now to proceed further, we need the values of, fine values of small signal BJT, small signal BJT parameters. We don't know the parameters values. BJT parameters. So we know that R pi will be equal to VT by ICQ into beta. So we already know that. So this gives us 2.6K. GM is 0.038. Basically IC by VT. So we know this here. R0 is VA by IC, DC IC, so it's 100K. So we know all these parameters now, right? So now RC parallel RL is how much? This is 1K. RC parallel RL, 2K parallel 2K is 1K. RB is 430K. So we have all the parameters in front of us. 430K. Alright. 430K. We have all the parameters. Okay, at this stage we note the following. This is R0 is 100K and 100K in parallel with 1K. 100K in parallel with 1K, why bother with R0? Right, so we remove this. So we simplify the circuit. Right, we simplify the circuit, and it's obvious what we have done circuits like this right in the beginning. So we know this is V pi. So we know that from here V pi is basically equal to Vs. We can see it here. V pi is nothing but Vs, and V0 equal to minus GM V pi If you want to be accurate, you can write R0 parallel RC parallel RL. You can do all of that, and therefore V0 by Vs equal to minus Gm multiplied by R0 parallel RC parallel RL. It's a very important result. V0 by Vs is minus Gm R0 parallel RC parallel RL. And so the final step is find values of resistance, solve the circuit. Right, we solve the circuit to obtain the parameters that we want. So what is the value of the gain that we get? V0 by Vs is minus 38. Minus 38. So this circuit that we have drawn here, right, this circuit that we have drawn here, we have put here RL, V0, put here VCC, we put here Vs, and we find V0 by Vs equal to minus Gm R0 parallel RC parallel RL. And for a particular value of combination, we got a value of, we can call this the gain of the circuit, AV. We got AV is minus 38. Minus 38. Voltage gain of the circuit is minus 38. This is one of the simplest amplifiers that you can make. We call this the common emitter amplifier. One of the simplest common emitter amplifiers that you can make. Right, simplest amplifier that we can make. Okay. Now, in an amplifier, so gain is one thing. So let me draw a amplifier like this, a diagram of an amplifier like this. In an amplifier, the gain is of course of interest. Also of interest, you're giving the input here and you're taking output here. Also of interest is the input resistance. Input resistance, Rn. And also of interest is, if this is the load, let me put a load here. Also of interest is, note that leaving the load, R0. So these are of interest to us. What is Rn? What is R0? So can we go back in the circuit and calculate what is Rn and what is R0? Go back here and see what is Rn. Rn is the resistance looking from here. Note that when you look from here, you see Rb parallel R pi. Alright, so Rn is Rb parallel R pi. per second. What is R0? R0 is looking from, actually now there's a little bit of trouble because we have merged RC and RL. So let me remove this merging of RC and RL. Let me remove this. Let's call this RL, and let's call this separately RC. Let's call this separately RC. And R0 by definition is looking from here. This is R0. So when you look from here, what do you see? You see RC, R0, okay? So you see R0 is RC. Now please do not confuse this R0, capital R0 versus this small R0. Small R0 is the output resistance of the transistor, and this big R0 is the output resistance of the amplifier. Amplifier is separate from the transistor. Okay. Now in most of these cases what you will find is RB parallel R pi. So this is practically equal to R pi. In many cases this is practically equal to RC. This is like R pi and this is like RC. So you know input resistance, you know output resistance, you know the gain of the amplifier. But note that the expression for gain that we have determined is with the RL there. With the RL there. If let's say RL is infinity, then we can call something called the open circuit voltage gain, AV0. So that would be equal to minus GM R0 parallel RC, right? R0 parallel RC. And this will be approximately equal to, most of the time R0 is very large, will be equal to minus GM RC. So that's the open circuit voltage gain here, AV0. Open circuit voltage gain. Open circuit, why? Because I've made RL equal to infinity. I've made RL equal to infinity. So what we have done, let's get back to this thing here. This is our amplifier. What we are saying is that this amplifier RBRC can be thought of as a block like this, with an open circuit voltage gain AV0 approximately equal to minus GMRC, with a Rn equal to basically R pi, with a R0 equal to RC here. So that's how my amplifier looks like this here. Now if you want to put an RL, we can put an RL, right? We can put an RL here. But my amplifier without an RL is like this. It's characterized by AV0, by Rn, and by an output resistance R0, which is equal to RC. Okay? We can represent, so what is the meaning of Rn? Rn is the resistance looking from here. which means that this amplifier, what we are saying is this whole amplifier is as if like this. When I look at it from the input side, this is, let's say, we call this input V in, is a resistance Rn. And when I look at it from this side, this is a voltage source AV0 times V in times R0. That's what we are saying. Actually, we're building R0. This whole amplifier is like this. This is plus minus V in, and this is plus minus. This is the meaning of these quantities. When you said Rn is what? Resistance looking from here. So our amplifier is, when you look at your amplifier, the amplifier appears as a resistance Rn, and there is a voltage across it which is V in. Okay, when you look at it from the outside here, when you look at it from here, what will you see? The gain. The gain you will see is, when it is open circuit, the gain you will see is AV0. AV0, so, or the voltage that you will see is AV0 times V in. So that's correct. The voltage gain is AV0 times V in. And if you want to look at the resistance looking from here, we said the resistance is R0, so this is R0 here. Right? So the whole amplifier looks like this here. This whole amplifier can be thought of now, after analyzing, can be thought of as Rn, AV0, V in, and R0. That's why we are finding this out. So now with this, if somebody tells you, so once you take an amplifier like this and you know Rn, you know AV0, and you know R0. For us, the value was Rn was 2.6K, R0 was 2K, and AV0 was minus 38. So we found these values out, right? Now somebody takes your amplifier, note that the same amplifier, what I do is, I don't have Vs, but I have like this here, Vs, and I put here 2.6K, and then I feed it into a capacitor, and everything else is the same. What will happen now? Do you go back and do the whole small signal circuit again? Or is there a simpler way? Right, so what we have done is we have modified our source. Source has a 2.6K resistor RS also. So do I do the whole thing? No. The thing is, note that this entire thing here and this entire thing has been represented by what? By this circuit. I don't need to do it anymore. I can connect any source here. I can connect any RL here and calculate. So can you tell me what will be the gain now? I put an RL of, now let's say RL of 1K. Tell me what will be the gain? V0 by Vs. You understand? Same amplifier, but we have put Vs and Rs of 2.6K and we have put RL equal to 1K. What will be the gain? Look at this circuit. This, everything in this red box, red circle, is this circuit here. So what do you have to do? You have to connect basically that we have said, you connect it here, right? And this is ground, right? That's the source that you connect here. And here, you put here an RL of 1K. That's it. And so what does the gain become? Gain becomes, so note the advantage of this representation, Rn, AV0 and R0. Does everybody see that the gain will become, this voltage Vs will divide here? Rn by Rn plus Rs, right? So that's Vin multiplied by AV0, fine, AV0, and then there is a voltage drop, RL by R0 plus RL, and that will give you the final gain. Right? I don't need to redo analysis if something changes. If this is the core of my amplifier, the rest is the signal and the load. The core of the amplifier we have characterized using these three parameters here: AV0, R0, and RL. That's the core of the amplifier. The load and the source have been kept separate. Right, so all of you can calculate now. Let me give you a related problem. Tell me, same block, $2K, 430K, Vs, what will be the gain? Q1 and Q2. What will be V0 by Vs? I've taken two stage. This is stage 1 and this is stage 2, and we have connected the two stages together, cascaded the two stages together. Remember what each stage looks like. Remember, this part you've already analyzed. This part, you know this, right? This we've already analyzed. From here to here, this block we already know. We know this. Similarly, this block is identical from here, here, and this block is also identical. We already know this. Each one of these blocks is, we said, is basically this. Remember, Rn, voltage source, AV0 times V in, whatever is this V in, this V in plus minus, and this R0. That's what this particular block is. This is R in, and this is V in. Each one of these blocks is like this, and we have the value of Rn. We calculated Rn is 2.6K, again R0 is 1K or 2K, and AV0 open circuit voltage gain was minus 38. So each one of these blocks is known. That's why we calculate AV0, Rn, R0, because once we calculate, we can use this in many places. So you have to put these two stages together and calculate. Check if gain comes out to be, overall gain comes out to be 408, is it? If my calculations are okay, 408. Is it 408 or what? Gain, huh? 408. Everybody please calculate. All that you have to do is substitute, instead of the amplifier, substitute this here, put the load, put the source. That's it. All right, everybody can do. Otherwise, let's have difficulties. If you're facing difficulty, tell me, where is the difficulty? Capacitors act like shorts. Shall I draw the circuit? The circuit would be like this, one stage, and then we will connect here. Let's do that. We'll connect here VS, then to the next stage is also like that, so we'll connect here. Next stage is also RN, and we'll put here plus minus AV0 times, let's call this whatever V in 2, or the output stage V, whatever you want to call it, AV0 times V01. This is again R0, and then is finally connected to 2K, and you get V0 here. That's it. The whole thing becomes like this. Starting from here, so VS, V in is VS. The voltage that appears here is AV0 times V in. There is R0 and there is Rn here, so half gets divided, not half, a voltage divider, that will give you V01, and once you get V01, you will get this value here, and then there is a voltage divider again, and you will get the final value that is there for V0. Note, otherwise, if we had not done this, then you would have gone back and written out the whole equivalent circuit again, long big equivalent circuit, and unnecessarily complications would occur. So use of Rn and AV0 and R0 helps to simplify the analysis and makes it easier. Okay. Let me ask you this, okay? Let's come back. This circuit, all of you have to understand very well. Go back here and this is the simplest amplifier that I can think of. What is the gain that we found? V0 by Vs is minus GM RC, GM RC approximately, right? After making the approximation that R0 is negligible here. Why is there a minus? What does minus represent? All right, 180 degree phase shift. This is of course coming from formula. What it is saying is that output voltage is 180 degree out of phase with input, small signal. How do we prove this? By looking at the circuit. Yeah, from formula it is coming, right? But from the circuit, is it coming? From the circuit, how is it coming? Qualitatively, can we do that and show that yes, phase is 180 degree? What does 180 degree mean? That if you make something increase, the other one will, right? So 180, you know, that we draw here. If this is input, then we are saying the output goes as output goes like this. Output goes opposite, right? So if this is increasing, input is increasing, the output is decreasing, right? That's what we mean by 180 degree phase shift. Before we do that, okay, let's do the following. So remember, RC was 2K, this was 430K, right? This was 430K, and let's take an example of where we assume Vs is equal to, let's say, 10 millivolt sine omega t, right? 10 millivolt sine omega t. For this, we had found that the gain was approximately equal to minus 38. All right. So we had done this analysis. Sorry, this is not V0. This is VCC, capital VCC, DC. VCC equal to 5 volt we had taken. Right. We had done this analysis. Can you all plot this? What is the voltage at this point? How will it look like at this point? I want to draw here and I want to draw here and I want to sketch as a function of time the voltage at this node. You are all seeing this is nothing but the base, right? At this point, what is the voltage? Say the 10 millivolt sine omega t had not been there. The voltage at this point would have been, we are doing DC analysis by assuming about 0.7. Now that we add this Vs, what happens? Vs also goes here. So the net voltage at the base, that's what we call it, net voltage at the base, Vb, is equal to the DC value plus a sinusoidal small signal value, Vb. Right? That's the net voltage. This voltage also goes here and there's a DC also. So DC value, how do I represent on this? So we are plotting VB. VB as a function of time. So how will it look like? The first part looks like constant, right? The first part looks constant. The first part, 0.7, approximately equal to 0.7. The second part what? VB is nothing but Vs. So it's sinusoidal. So there's a little bit of sinusoidal like this, like this, like this. Right? I'm probably exaggerating. And the magnitude of this is, we said, this is nothing but 10 millivolt. That's how the net voltage at this particular point looks like, right? It has a DC, and then you add on top of it the incremental. Vs is nothing but incremental, it causes changes. Now, similarly, if I were to plot at the output, collector would also have, note that the net collector voltage, Vc, will also have a DC value, capital DC, plus a small signal, this thing which is small signal collector voltage, which is nothing but same as V0. Right? So if I were to plot here again as a function of time, what do you think will VC look like? VC would look like, what was the DC value of VC? 3 volt, right? So you draw 3 volt. 3 volt. This is 3 volt. And then what is this value here? This is nothing but equal to V0. And V0 is what? Equal to the gain minus 38 times Vs. Minus 38 times Vs. So where will it go? How will it look like? It would look like this. It would look like this and this and this. Right? What is this magnitude equal to? 38 times 10. So 380. This is about 0.38 volts. 0.38 volts. So what is the minimum value of collector voltage? Minimum value of collector voltage, VC. Can you tell me this? VC minimum? Minimum value of collector voltage, VC min, will be how much? Collector voltage, it's the sum of, so it would be 3 minus 0.38, right? This is the minimum value here. 3 minus 0.38 will be 2.62 volt. Minimum value. Maximum value 3.38, right? So the collector voltage here is going down and is going up and going down and up. When we put a capacitor, what the capacitor does is it removes the 3 volt from it and just leaves the 0.38 sinusoidal. That's what the aim of the capacitor is, just to remove the DC, and then it leaves you only with the AC value here. Right? So note that what we are saying is the following. Let me reframe the question. What we were saying is, why is there 180-degree phase shift between V0 and Vs? Why is there 180? You can see here, when this is going up, this is going down. Why? Can you understand where is the phase shift coming from? Why is it coming? Apart from the formula. No, capacitors are acting like shorts at the signal frequency. Capacitors are acting like shorts, which means they're not introducing any phase, nothing. It's not that.
If VB increases, then IB increases, and then IC increases, so VC decreases.
Right, so that's the answer. See, what he's saying is the following. If I look at this particular node here, this particular node is, the voltage is increasing, right? Voltage is increasing. If the voltage here increases, right, what does it do? It causes, if the voltage increases, note that this is the base emitter junction. If the voltage across the base emitter junction increases, what does it do to the base current and the collector current? It causes, basically, the collector current depends on the base current, this thing here. So if this voltage increases, then it will cause current here, IC, to increase, because the voltage here is increasing, so the collector current here increases. If the collector current increases, then what happens to this voltage here? The drop increases, so the voltage here, VC, goes down, and you can see the 180-degree phase shift. An increase of the voltage here causes increase here, causes a decrease in this. That's the source of 180-degree phase shift. So without going through the maths and minus and all of that, one can see that there is 180-degree phase shift between the input and the output. let's stick with this circuit. There are a lot of interesting things one can try and understand about the amplifier, about a common emitter amplifier. It's a simple circuit, but alright, so gain is AV equal to minus GM RC. Okay, minus GM RC. And we got a value of minus 38 for some combination. How can I increase the gain? Increase gain. What would you do? What are the strategies for increasing gain? Alright, he's saying increase RC. Anything else? There are only two factors, so obviously you should say increase GM. But what is GM? IC by VT. We are not changing temperature and all that, so it implies that increase IC. Increase IC. So how do I increase IC? Okay, so this implies, you're right, IB is VCC minus 0.7 by RB. So what I need to do is I need to, for example, reduce RB. If I reduce RB, what it will do is increase IB, it will cause increase IC, will increase GM, and then the gain will increase. Correct? These are the two ways in which you could go about, for example, changing the gain. So let me ask then the following. Fine. If AV increases, okay, let's look at the first strategy. AV increases. Does anything happen to Rn? Input resistance. Remember what was Rn for this? Rn, let's write down. So Rn was approximately equal to R pi only, and R0 was RC. Is there any change in Rn when you employ the first strategy? When you employ the first strategy, is there any change in Rn? Huh? Rn is R pi. Did I touch my IC? R pi depends on what? IB and all that. Did I touch all that? No. No change in Rn. Rn remains the same. Rn remains the same. What changes? Does R0 change? R0 increases. Okay, R0 increases. Is an increase in R0 good or bad? Do you want, see, AV, high AV, you all agree, large AV0, right? So let's call this, we are talking about AV0 actually, AV0 here. So AV0, open circuit voltage here. So high AV0 you all want. What about R0? What do you want from R0? A low R0 or a high R0? Remember, this is a voltage amplifier. We are making a voltage amplifier. So what do you want from R0? What should I look from R0? Gain is obvious, large gain. What do you want from R0? Why low?
First, power dissipation will be more. Also, for higher, the voltage drop across R will be more.
Okay. So the answer for this is actually comes from the diagram. Remember we said this amplifier diagram, what is it? We think of it like Rn AV0 times Vin and R0. That's what this amplifier looks like. Any amplifier will look like this. Sorry, I drew a diode. not a diode but an amplifier. It looks like this. Let's put a common terminal here, so common ground here. If I put here, so this is my ground here. So note that if you look at this picture here, you know, you want a small R0, because when you apply V in, when you apply some voltage here, V in, it appears across this, fine, and then it goes here, AV0 times V in. Then you want this voltage to go to the load, right? You eventually want it to, you will connect some load here. Eventually you will connect a load here. You want this voltage to go to the load, and therefore you don't want it to drop across R0, right? So you would like R0 to be small. R0 should be small. You're looking for that. A small R0 is desirable. Large R0 means that this voltage will get dropped here only and will not appear across RL. Right? R0 should be small. What about Rn? Rn should be small or high? Why is that?
There is a in voltage, so there will be some resistance.
So for example, right, so that's what, yes, for example, if I have a voltage source, you're right, if I have a voltage source and I connect an RS here. Now, for signal to get amplified, I want this Vs to appear here, Vs to go to Vn, right? Then only it will get amplified. I don't want it to drop across RS. This will only happen if the resistance looking from here is much larger than RS. So you want Rn to be high. Now how high do you want? Well, Rn should be much larger than RS maybe. Whatever RS you have, it should be much larger than that, so that all the signal Vs appears over here. Right? So note that what you are, from a voltage amplifier, what you're looking for is, you're looking for high AV0, you're looking for high Rn, and you're looking for low R0. These are the things that you're looking for from an voltage amplifier. Large AV0 is obvious, large Rn and small R0. So if somebody tells you the following, somebody tells you, I have two amplifiers. One amplifier is here, AV0 is equal to minus 100. Another amplifier is here. AV0 is equal to minus, say, 25. Which amplifier is better? One is 100, the other is 25. Which is better? Which amplifier is better? How do you say 100 is better? Gain is? Okay, so that's what the point is gain the whole story in an amplifier. Is that the only thing in an amplifier? Is gain the only thing in an amplifier? AV0, open circuit voltage gain. Is that the only thing? What did we just say in the previous slide? We need Rn is also important. R0 is also important. So without giving you the value of Rn and R0, how are you saying one is better than the other? How are you saying one is better than the other? For example, let's put an artificial case. Let's say Rn, just arbitrary, let me put it, say Rn is 100 ohms. Okay, now let me add this. Rn is 100 ohms, R0 is 1k. Okay, and let me add in the next case, AV0 is this much, Rn is 100k, and R0 is 10 ohms. All right, let me add now. You still say one is better than the other? One is better than the other? Now that we add this additional, so these are also important. These are also important. We can always construct a situation. Let's construct a situation. Can you construct a situation in which let's call this amplifier A and let's call this amplifier B. Can you construct a situation in which amplifier B gives you higher gain? Note that this is not the final gain. This is open circuit gain. Can you construct a situation in which amplifier B gives you higher gain than amplifier A? Can you construct a case? B gives you higher gain than amplifier A.
Yes, if let's say RS is around 1k.
RS is around
1k.
RS is around 1k. Yeah, do that. And R0 is RL is. It's very easy to construct a case. For example, suppose I have a source, as he's rightly saying. Suppose I have a source like this, Vs, and what were you saying? RS, let's use as
1k.
Okay, 1k, and in between load on the other hand, suppose I use a load of 100 ohms. Okay, let's use a load of 100 ohms, RL, right? Then I take my first amplifier and I put it here. First amplifier, I put it here. So first amplifier I put here, I connect. My first amplifier is like this. Amplifier A. What is the overall gain it gives me? V0 by Vs. Now calculate. V0 by Vs, what will it give me? RS is 1k, Rn, so note that if I calculate, it will give me 100 divided by, you guys also do it, divided by 1100 multiplied by gain of 100 multiplied by RL 100 by R0 plus RL, so 1100. So this is what it will give me. Overall gain, it will give me 100 by if the calculation is correct, in fact it doesn't give me gain, it gives me 0.82. This amplifier does not give me a gain at all. Open circuit gain was 100. Now I use it in a particular situation where my source resistance is 1k and load resistance is 100 ohms. It doesn't give me a gain. It actually attenuates the signal. It attenuates the signal. On the other hand, if I put the other amplifier, please check that this analysis is correct. If I use amplifier B would give me 100k and 1k, so it's almost like 100 by 101 into 25 into RL is 100 by 110. So I think So this gives me 100 by 110 into 25, roughly 22.7. 22 multiplied by 22.5. The second one gives you an overall gain of 22.5. Right? We can easily construct a situation like this. You can also construct a situation in which A gives you more gain. In which A gives you more gain than B. So which amplifier is better than the other is not decided entirely by AV0. AV0 is not the only thing. You have to look at Rn and R0 and Rn and R0. An amplifier with a lower open circuit gain can be better than an amplifier with higher open circuit gain. So all three are important figures. AV0 is important, Rn is important, R0 is also important. All three are important. Right? All three are important for us. So in that case, let's go back and look at this. Remember this diagram? Yes, let's go and look at this. So all of you said that if you want to increase gain, one of the ways of increasing open circuit gain is increasing RC. Fine. So, and you know, we write increase in RC will cause an increase in RC is causing gain to go up. Fine. Rn doesn't change, but R0 also goes up. So are you seeing what has happened? You improved the gain, but what did you do? You made R0 back. Right? You made R0 back. What about the second approach? In the second approach, what are you doing? You're changing IC. You're saying I will cause RB to decrease. RB to decrease will cause IC to increase. Will also cause AV to go up. Will also cause Rn to. What will happen to Rn? If IC goes up, Rn is R pi. R pi is what? Vt by IC cube. So Rn actually goes down and R0 remains the same. So again you improve the gain, but then this time Rn goes down. See, you don't get anything for free. If you try to improve the gain, well, the input resistance either goes down or the output resistance goes up. Either one of them becomes bad. So what it is showing you in any design, that there are trade-offs. There are these trade-offs that are there. Trade-offs. You try to improve one quantity, the other quantity goes bad. So you can improve gain by compromising output resistance, or you can increase gain by compromising input resistance. Either one of those things that you could do. These are the possibilities. Now, on the same theme, note that, so that is the, so you all realize that AV is important, AV0 is important, Rn is important, and R0 is important. For our amplifier, AV0 was minus GM RC, Rn was R pi approximately, and R0 was RC. Can you see a relationship between them? Suppose I do the following. AV0 into Rn by R0. What do I get? If I multiply them together, AV0 into Rn and divided by R0, what do you get? Let's put the magnitude here, magnitude of AV0.
Beta into VT.
Think about, think carefully, what do you get? Beta. This gives you beta. A very important equation. What is this equation telling you? This equation is for this circuit, right? This equation is for this circuit, a common emitter amplifier, right? This circuit, common emitter amplifier, and we are finding this. What does this equation tell you? What is the importance of this equation? A transistor with a higher beta will allow you to make a better amplifier, you are saying. Why? Because normally, what do you want from AV0? You want a high value of AV0. What do you want from Rn? Higher value. And what do you want from R0? A smaller value. So in effect, what are you asking? I need a higher value of beta. A large value of beta will allow you to make an amplifier with better gain, better input resistance and lower output resistance. It shows you the importance of beta. And this shows you the trade-off. It shows you the trade-offs. Now once you select a transistor, whichever transistor, beta is fixed. Whichever transistor you select, a transistor with a beta of 100 or a beta of 50 or beta of 200, the beta is fixed. Once the beta is fixed, what does this equation tell you? If you try to increase the gain, you will either lose Rn or you will lose R0. If you try to increase the gain, either you will lose Rn or you will lose R0 because the right hand side is a constant. Right hand side is a constant. Right? It's telling you this is the signature of a common emitter amplifier, that the open circuit gain multiplied by input resistance divided by output resistance is a constant beta. And it's telling you the importance of beta. Try and select a transistor with higher beta. Will give you better characteristics. Okay? All right. What is the drawback of this amplifier? Can you see the amplifier that we have just drawn? Let's just draw this amplifier. One very simple amplifier. Very simple amplifier, but it has certain drawbacks. Now, if you start with, okay, let's see, AV0 is minus GM minus GMRC. Okay, before we do that, somebody comes to you and says, design a CE amplifier with a gain of open circuit gain with a gain of AV0 equal to minus 50. Design a circuit with a open circuit gain of minus 50, and he says, but supply voltage, I want to run the whole thing on a pencil cell 1.5 volt. Would you be able to do it for him? He says, give me a gain of minus 50, open circuit voltage gain of minus 50, but I can only run my amplifier on 1.5 volt pencil cell. Do you think you can design this amplifier for that person? Would it be possible to design the amplifier for that person? Is the design possible? That's the first question that we have to ask. Is the design possible? If it is possible, then we'll go ahead and find out RB, RC, right? The only thing that is left is RB and RC. RB, RC, and a choice of transistor. Provided the design is possible. It may be that somebody is asking you for something and the design is actually not possible. How do we check that? All right, what do you conclude? Is the design possible? Before finding RC and RB, is the design possible? Note that what you need to do is take this equation and write it. What is this equation? Minus GM is ICQ by VT times RC. If you want a gain of minus 50, this implies ICQ RC equal to 50 times VT. 50 times VT is 1.3 volt. VT is 26. 26 multiplied by 50 is 1.3 volt. So ICQ RC is 1.3. What does this imply? VCE equal to 0.2. What does this imply? Transistor in saturation. In saturation, transistor never amplifies. Is design possible? The answer is no. It's not possible. So somebody comes and asks you to design an amplifier which will run on a gain of, which will give you a gain of 50 on 1.5 volt. You say no, it's not possible. Is that true? Not possible? Well, not exactly, right? You made an assumption that it's a single stage amplifier. He doesn't care. You could always do the following, right? You could always add 2 stages. Right, at 2 stages. V0. He is not saying, he's not saying that, he's saying give me a gain of minus 50. He's not saying that use only 1 stage. He's not saying that. Use only 1 stage. You can use 2 stages. Use a 2-stage amplifier. So you are right, 1-stage amplifier will not work. That we have found. 1-stage amplifier will not work. But 2-stage amplifier may work. Right? 2-stage amplifier may work. So you want AV0 of, he wanted AV0 of minus 50. Well, this becomes a little bit of a problem if he insists on minus. Are you seeing? If the person insists on minus, the first stage gives you what? 180 degree phase shift. Next stage also gives you 180 degree phase shift. Total phase shift becomes 0. But I think by and large, the minus would not be such a problem. Okay. So let's say gain is 50. AV0 is 50. Now what will you do? In general, this need not be true. So you'll put RC1 here, RC1 here, RB1 here, RC2 here, RB2 here, and now you will have to decide how will you design this amplifier. Note that if I tell you for a stage like this, if I tell you AV0 and I tell you Rn and I tell you R0, would you be able to design the amplifier? For a single stage, would you be able to do? Yes or no? Let me give you a homework problem. Okay. Homework problem is this.
So for a single stage.
Single stage, yeah. Homework problem is the following. Here, here, here. This is standard single stage, RB, RC, V0, right? Single stage here. And what I'm saying is design an amplifier which will give us AV0 is minus 100, Rn of 1K and R0 of 1K. Do this design. Design the amplifier. Now, when you design the amplifier, you have to give me the following. you have to give me what is happening. You have to give me the following. Obviously, you'll have to give me RB, you have to give me RC, then, sorry, this is not V0, I keep making that mistake here, this is VCC. You have to give me the value of VCC, and you have to tell me what kind of a transistor do you want. So basically, what kind of beta do you want? If I have these things, maybe I can go ahead and design the amplifier. RB and RC I can select in the lab, VCC is also there. If you tell me I need a beta of 50 or 100 or 250, I can go ahead and choose amongst the many transistors that are there, that particular value. Now remember, don't try to unnecessarily use a very large value of beta, because that transistor will be costly. Okay, so use a beta which is reasonable. Okay, so now the issue is find the value of RB, find the value of RC, find a suitable value of VCC, find a suitable value of beta, and tell me, then we will get a design of this simple common emitter amplifier. Correct? You have all the equations with you. You have the equation for AV0, you have the equation for Rn, you have the equation for R0. All the equations are available, and you should be able to do all of these things that you see. Okay, so do this design as a homework problem here. Homework problem. Okay. If you come back to this amplifier, and that's what you were saying, if you come back here, this amplifier here, look at this amplifier. AV0 we said is equal to minus GMRC, equal to minus IC. Sometimes we use the word Q to refer to quiescent point. These are DC by VT, right? AV is minus. If you look at Rn, we said Rn is VT by IC, Q multiplied by beta. If you look at R0, R0 is RC. Okay? If you look at these quantities, all these things, AV0, Rn, R0, they all are affected by, maybe not R0, but at least AV, Rn, R0. In general, the transistor characteristics are affected by ICQ, which we call as the bias current. This is the bias current, DC bias current. They are affected by it. ICQ determines AV0, ICQ determines Rn, and many other things. We have not looked at lower cutoff frequency, upper cutoff frequency. It determines all of those things here. Okay. So in general, the amplifier, this is just an example. In general, the amplifier characteristics right? Amplifier characteristics are affected by bias point. Where is my transistor biased? DC bias point. DC bias point. Any change in bias point, what will it do? Will change the amplifier's characteristics. Any change in bias point will change the amplifier's characteristics. So this is obviously telling you is you want a stable bias point. Stable bias point is important. stable bias point is important. Right? You want bias point to be stable. If the bias point is not stable, if the bias point shifts, then everything of the amplifier shifts. Everything of the amplifier depends on the bias point. Right? Now the issue is, why would bias point change? What will cause bias point to change? What can cause a bias point to change? Well, let's go back to this amplifier again. I'll keep drawing this amplifier several times. So, what can cause this bias point to change? So, let's look at the bias point. For bias point, I need not draw the AC part here. VCC, RC, RB. So, bias point, as you all know, if I write IB equal to VCC minus this base emitter voltage, let me write down as VBE, base emitter voltage of the diode voltage, divided by RB, and IC is beta times IB. So we are interested in this IC. What can cause my IC to change? There are several things. Any change in supply voltage, VCC. You know, you have a supply voltage, say it's supposed to be 5 volt. Supply voltage could increase a little bit. Instead of 5 volt, it could go to maybe 10% higher, 5.5, 10% lower, 4.5. So supply voltage could change. It's sensitive to supply voltage. Any change in supply voltage will affect IC. You can see here. Any change in supply voltage will cause IB. Any change in IB will cause IC. So VCC is one. What else do you see? Resistance, and so I've put a resistance, RB and RC. Now there are two ways in which RB and RC may change. There are two ways. One is temperature. A change in temperature will cause RB and RC. All these resistors have a temperature coefficient. A change in temperature will cause my value of the resistor to change, and therefore the value of IB to change and everything else. Now temperature has two things here, right? So let's put here, temperature causes RB and RC to change. Another thing that the temperature causes is it causes this VBE, diode voltage, to change. This diode voltage here that you see here, this causes it to change. We saw that earlier. Temperature causes beta to change. Beta in general increases with temperature. So temperature has all these effects that you see here. Temperature has all these effects, right? And then finally, what has an effect is, okay, so the resistors, we said temperature affects this, which will, I'll come in a minute. The beta is a source of instability. Beta is a source of instability. How? Well, note that you have, obviously you can see IC depends on beta. Right? IC depends on beta. Let's say you've done a design. We saw a design earlier. Where RC was 2K and RB was 430K and VCC was 5 volt. Right? This was our design. Right? One particular design. And we were assuming beta equal to 100. Right? This was a design. Now, a manufacturer is not going to make one amplifier. Let's say you are in the business of making amplifiers. and you're making, n number of amplifiers. N number of amplifiers. Nobody's making one amplifier except in the lab. If you have an exam or something, or you're doing an experiment, you're making one amplifier. If you're a manufacturer, you're making n number of amplifiers, maybe 1 million units of amplifiers. Right? In all those amplifiers, what is fixed? The design is fixed. In all of them, you're going to use RB of 430K, C of 2K, and beta of 100. So these resistors. But all of you know that the resistors have what? Resistors have tolerance. You pick a resistor of 2K in the lab, 2.2K. It's not going to be 2.2K. It may be a little higher than 2.2K. It may be a little lower than 2.2K. So that's how the resistors change. When you guys said RB and RC change, how do they change? Well, even though the values are the same that is written there on the resistor 2.2K, the values are a little higher and maybe a little lower. So that's how RB and RCs are changing. From one amplifier to the second to the third, no amplifier will have exactly same value of RB and exactly same value of RC. If the tolerance is 10%, then the resistor values are going to change by 10%. Instead of 2K, instead of 2K may become 2.2K, or 2K may even become 1.8K. In a particular amplifier, even though your design says 2K, you may get 2.2K or 1.8K. If you get 1.8K, what will happen? You get lesser resistance, then what will happen? Instead of RB of 430, you get lesser resistance, the current will go up. In that particular amplifier, IC is a little higher. So ICs, so you are seeing the instability is being caused by that. So these resistor values are changing. They are not the same. Now you may say, well, I'm not going to use 10% resistor. I'm going to use 1% resistor, where the tolerance is 1%. Now I have a very stable design. But 1% resistors are much more expensive. Something that you can control very well within 1% is going to be more expensive. Something where you let it vary by 10% is going to be cheaper. So there's a price that you will have to pay. If you use a 1% resistor, that will turn out to be expensive. But amongst this, what happens is, in different amplifiers, you will use different transistors. Obviously, you're making some 100,000 and 1 lakh amplifiers. In each amplifier, you will have a separate transistor. Now, it turns out that beta varies a lot. The manufacturer may say, I have made 2 identical transistors. Right? Manufacturer is writing the name of the transistor is what? Let's say 2N222 or 2N234, whatever, made using the same process. One transistor may have a gain of 100, another may have a gain of 150, third may have a gain of 200. It varies a lot. The gain, one does not have a very good control on beta. So what would happen? You have done a design assuming a gain of 100, right? And so you get 1 milliampere, right? 1 milliampere here. But the same design, same transistor, supposed to be same transistor, but its gain turns out to be 200. Its collector current will become double. Collector current will become double. Maybe the gain may become double. So the person asks for a gain of 50, he will get a gain of 100, AV0, but he will get Rn of half. So you're saying that beta varies a lot. And because beta varies a lot, IC will vary a lot. And so this design that you see here is not very useful. In that sense, it's not very useful. You have to make lots of amplifiers, and if beta is varying so much between 100 and 200, then the bias current will just go here and there. Will change by a factor of 2. And this amplifier is no longer, it's not useful then. because the bias point will change, gain will change, input resistance will change, everything will change. So as a manufacturer, you want to say all my amplifiers will give me a gain of 100, input resistance of 1K. You will not be able to say anything. One amplifier may give you a gain of 100, another may give you a gain of 200, but input resistance of half. Right? So this is the problem of this particular circuit. When we say we want the bias point to be stable, yes, we want the bias point to be stable due to VCC. A change in VCC should not cause a change in IC. A change in temperature should not cause a change in this thing. But even more serious than that is the change in beta. Beta will change a lot and causes a circuit to bias point to become change with the value here. So what we are looking for is a beta insensitive. One of the goals is beta insensitive biasing. We are looking for beta insensitive biasing. Similarly, you may look for VCC insensitive biasing, right? This is another goal. Supply voltage. So one goal is beta insensitive biasing. Another goal is VCC insensitive biasing. Third goal is temperature insensitive biasing. You want all this because everything depends on biasing. You're looking for all of these things. So, but the first thing that we need to look for is if it's so sensitive to beta. See, temperature will change, but the effect of temperature change is what? Effect of temperature changes, maybe RB, RC will change, VBE will change, and again beta will change. If I make my circuit beta insensitive, even if beta changes due to temperature, it's not going to change much. Now, VBE will change. Now, a change in VBE, if VCC is large, let's say this is 5 volt, a change in VBE here may not cause a very big change in IB. Right? So these things to some extent can be managed. To some extent I can manage temperature insensitive biasing. Supply voltage we have to see that, but this is a very serious matter here. I have to make a beta insensitive biasing. I have to bias the transistor, but it should not be sensitive to beta. And so so this is where, okay, so let's stop here and we'll continue from this particular place here. So we'll continue from beta insensitive biasing here.